Okay, we'll get started. Thanks everybody for showing up. So my name is Ginger Scoggins. I'm actually ASHRAE President-elect. For purposes of this presentation, however, I was chair of the ASHRAE Building Ad Hoc Committee for our renovation project that we're going to do a case study on today. I'm going to talk a lot about... Okay, can you hear me now? Is that better? Oh, okay, good. Well, let me try that again. For purposes of this presentation, I was actually chair of the Building Ad Hoc Committee for ASHRAE for this project. So I'm a volunteer with ASHRAE, just like a lot of you in the room are, consulting engineer by trade and also a commissioning agent. And so I was tasked with leading the volunteer team of ASHRAE members that oversaw this project from beginning to end, right? So this started in about 2018 with this project. ASHRAE was trying to figure out what we needed to do with our existing building, and so I'm gonna walk through that. I'm gonna kind of do a high-level overview of that process, and then I'm gonna turn it over to Ken to really get into some of the details of the control system for the project. So this first slide obviously shows that we are engineers because we can misspell words. So this is supposed to say renovation of ASHRAE building headquarters. And this is just a slide that they want us to add to say that this gets AIA credits. And the course description is on here as well as learning objectives. So we'll get started with the agenda. We're going to go a little bit into the background, the project goals, execution, some lessons learned, and then I'm going to turn it over to Ken to talk about the control system. So a little bit of background. So I'm not sure how many people in the room are ASHRAE members, but ASHRAE's headquarters is in Atlanta. We have about 100 staff members in Atlanta that were in a building. That's the building here that's shown that we sold because we went through a lot of iterations on what we should do with this building, but the issue was that Children's Hospital of Atlanta was building a huge campus, and our building was going to be almost dead in the middle of it. And so we didn't really want to live in a 10-year construction project with our building. We had just renovated our building in 2010, so it was a LEED Platinum building that we were using as a showcase building. But because of the Children's Hospital of Atlanta and what was going on there, we decided to go ahead and sell. They made us a very good offer. It was higher than the estimated value of our building. And so we decided to accept that offer and move. And we did that after looking at options to rent or to build or to renovate. And we ended up with a new building, with an existing building. It's a little bit outside of Atlanta in Peachtree Corners. It was almost double in size and on 10 acres of land. And so we got a really good deal on this building, but it was a 1970s building, okay? So we had already renovated our building to be a LEED Platinum building, and now we were moving into a 1970s building that had been abandoned for a year or so before we bought it. So we purchased this building in December of 2018, and we started talking about what our project goals were. So, you know, we looked, like I said, at building. We looked at leasing. Leasing is not really in ASHRAE's DNA. And in Atlanta, if you lease a building, I mean, you're paying $30 to $40 a square foot to lease a building. It was going to be quite a bit of money over time to lease a building. We did look at building a new building. We had an opportunity to build a new building on a brownfield site because we were trying to show some environmental stewardship here. We put both of these options in front of our board of directors, the renovation of the 1970s building or build a new building. The board of directors decided to go ahead and renovate the 1970s because what we're trying to show is you can take an older building, you can make it net zero. There are some lessons learned here that I'll go through in a little bit on that process, but it needs to happen. The building stock that's in use in 2050, they say that at least half the buildings that are going to be in use in 2050 have already been built. Most are not performing as they need to perform, as we all know. So renovating an existing building we felt like was good stewardship of what we should do in our industry. So we started with our ad hoc having a technical advisory subcommittee, and that technical advisory subcommittee developed our owner project requirements. So we had a very strong owner project requirement document that we submitted to our design teams before they decided they were going to pursue the project, okay? So as you can imagine, pursuing a project for ASHRAE would be a little daunting if you're a design engineer in this industry, right? I mean, fortunately, we had a lot of responses. We had some really good teams that responded to our RFQ. We had a very strong requirements in this owner project requirement. As you can see here, our mission critical items. Safety is number one, obviously. Affordable, we had to work within the budget. We had to meet or exceed our ASHRAE standards. Acoustics, so one of the issues in our existing building was that everybody was so tight that there were a lot of acoustical issues and concerns, and people were scared to even talk because their neighbor would get mad at them for making too much noise. So we really had to work on our acoustical levels in our new building, and we wanted to be net zero energy ready. So we felt like at the time with our budget, we did not have sufficient money to put our photovoltaics on the building. So we wanted to be ready, and we were looking at maybe a leaseback option for the photovoltaics on the building instead of purchasing them ourselves. And we weren't sure how that was going to end up. So we knew we wanted to be net zero energy ready. These are some other items in our OPR. We wanted to exceed our requirements of ASHRAE 189.1. We wanted our energy consumption to be at a goal of 21.4 kBTU per square foot per year. That's pretty low. We had a stretch goal of 15 kBTU per square foot per year. Our water efficiency, we wanted to meet all of the lead points. Our daytime plug load, that's actually supposed to be 0.4 watts per square foot, not 0.04. Acoustics, as you can see here, our outside air rate, we wanted to be 30% better than ASHRAE 62.1. We wanted demand control ventilation, obviously, for outside air control, and daylighting. We wanted most of our occupants to have access to daylight 55% of the time. And resiliency, we had a big resiliency discussion on our resilient goals and throughout the project and how we were going to meet those. And it was decided that if something happens in Atlanta, people are going to go home. So we really didn't have a resiliency need to house people overnight. So there was actually a generator on this project when we bought the building, and we sent that away. First of all, we didn't want to use any gas. We wanted to be carbon-free in terms of our usage of gas in the building. So we got rid of the generator because we figured if anything happens, people are just going to go home. That was our resiliency. We also have all these standards that we needed to meet, right? So we had ASHRAE standard 90.1, our energy efficiency standard. We had 55, 62, 189. Guideline 0, Guideline 1, we had commissioning agents on the project. They were brought in. We interviewed for commissioning agents after we selected our design team. And we knew we had to meet these requirements, and we also have a small data center in the building that we needed to meet that requirement, and we needed to also meet our advanced energy design guides. So those were our criteria for our design team, and people still submitted to do the project, which was fantastic. We had an initial construction budget after the purchase of the building of about $8.5 million. $130 a square foot is what we had estimated, minus donations. I mean, we are ASHRAE, so we did have a lot of equipment donations, so this did not include the equipment donations, nor did it include the PV. We set our project schedule. We had to move out by October of 2020. CHOA had bought our building, but they had given us a year lease free to stay in the building while we figured out where we were going to go. So we had to be out by October 2020. We obviously had to meet our OPR requirements, and then we hired the right team. So for the project execution, our architect did I think if there's a shining star in this project, I think it's our architect. He did a really good job of walking us through how to get this building to as low energy use as possible. Hopefully everybody here in the room knows that when you renovate a building or we build a building, the envelope is key to your energy consumption of your building, right? The envelope, and so many times it gets pushed back to the engineers, but it's not us really. We start with a good envelope and work your way down from there. So he did this graph, which I think was great, and it showed that for climate zone 3A, which is what we're in, the benchmark for offices is about 58 kBTU per square foot. If we took our existing envelope and we met ASHRAE 90.1 2016 on the HVAC, we would drop to 36.9 kBTU per square foot. If we improved our envelope to meet 90.1, then we would drop to 31 and on downward, right? So we reduced our window to wall ratio because our window to wall ratio was high. That would drop us down further. If we got to the recommended envelope that he recommended, then we would get to 27.3, which was better than the 90.1 envelope. Natural ventilation dropped us down even further, and then we got down to a high-performance HVAC system. So you can see that we dropped, close to over 30 kBTU per square foot just by getting the envelope under control and making sure our HVAC system just met the 90.1 requirements. This was a graph that he provided also that showed kind of basically a cost versus benefit analysis for the envelope. He went through several different envelope selections, looking at triple pane glazed windows versus double pane, where the cost, does that help you more? Is it worth the extra money? We ended up saying no, it was not. We ended up with the double pane windows. Our existing wall performance was an R3. Shows how bad in the 70s those buildings were built. It was an R3. We actually had a pressure test done before we renovated the building, and we were told that we had enough holes in the building that if it was one big hole, you could drive a truck through it. So that's how bad the envelope was for the building. So his recommendation was that we went with an R17 wall, an R35 roof. We ended up changing out all the windows. They were 1970s windows, kind of curtain wall windows. We changed all those out, reduced our window to wall ratio, and got our infiltration. Our goal was 0.011 CFM per square feet. We didn't quite meet that when we did the final pressure test, but we were definitely better than we were when we started. This shows our existing window to wall ratio. If you could remember from that second slide I showed, it was a curtain wall, continuous window to wall. And so we needed to get that down in order to meet 90.1. So we got the window to wall ratio down to 33.5% on the east and west and 41.9% on the north and south in order to meet the requirements of 90.1. So, we looked at different things like in order to increase the daylighting, raising the windows up so you got daylighting more into the space, or changing some of the configuration on the windows. But this ended up being the most cost-effective option. It met our goal of daylighting 55% of the time. And we ended up also adding skylights. We have 18 skylights throughout the building that we added to get our daylighting in place for all the occupants. So, like I said, this is the recommended envelope that we ended up with. You can see the new skylight that he's showing there. We had an R17 wall, R35 roof, and a 0.04 for the U value for the windows. And we ended up with an average window to wall ratio of 32%. We did have overhangs on some of the windows to help with some solar gain. And we got our infiltration down. So once all that was done, then we started talking about HVAC systems. Our design engineer, we had already decided as a team on our ad hoc that we were not going to pick the HVAC system. We have a lot of opinions, as you can imagine, on our ad hoc team and a lot of different thoughts on what type of system to go with. But we had hired a design team for a purpose, and we were going to let them make the decision, and we were going to, as we always do, critique it, right? So they actually came back to us with two options. The first option was an all-air heat pump option with heat pumps on the roof and with basically thermal diffusers in the space. There's several brands out there. I won't mention names, but so you have individual zone control through the thermal diffusers. So that was an option that was actually very affordable and got us down below our goal of kBTU per square foot, right? So it was a very affordable option. The second option was a hydronic option with radiant panels and DoAs units. And being ASHRAE, we were like, gosh, everybody can do a heat pump, rooftop heat pump system. We need to push the envelope, right? We're in Atlanta, come on. So it was pretty close to $1 million adder, but our team took a vote and decided that we were going to do the hydronic system. So I said we're in Atlanta, right? The thing about Atlanta was that nobody really had done a lot of hydronic systems in terms of radiant panels. Everybody does hydronic systems, but radiant panels, our contractors, we felt like, really added a premium on this pricing because there was a lot of not understanding how simplistic this system can really be. Because you don't, instead of all the ductwork you're running, right, you're running piping, but it's not large piping. And so there was a premium added. So, radiant panels in the South, they can be used easily. You just have to separate the outside air from the radiant system so you get rid of the latent load. And so that was what was happening. That's what we did on this building. So this is what we ended up with. We have 2 DoAs units on the roof that handle our outside air and deliver it at a neutral condition to the space. It is not connected to our hydronic system. It is a DX DoAs, both of them are DX DoAs units. We have a 4-pipe system with a water-cooled heat pump chiller outside. That heat pump chiller, if you've never used one, it has ours has 3 modules. They're like 20-ton modules. And so one module can be in heat, the other can be in cooling, or they can all be in heat or all be in cooling, depending on what the needs are of the system. I've got a better graphic here in a minute that shows the hydronic piping. So this is kind of what we ended up with. And we have ceiling fans. So that's the other thing to think about. We raised the temperature, the design temperature in the space to 78. With ceiling fans, because studies have shown, right, if you've got air movement, it can be a little bit warmer. So we could save some energy by having the ceiling fans and keeping it 78 in the space. The ceiling fans are tied to the BMS system. So they slow down or speed up as the BMS system requires them to do so. This is our hydronic piping system. This is what I was talking about a minute ago. We have the outdoor air-cooled heat pump chiller. We have a 4-pipe system in the mechanical room as our primary loops, right? We have primary cooling, primary heating, and buffer tanks, and all of that goes to the heat pump chiller. We pull off of that for basically the zone heating and cooling with the radiant panels. So we have 6-way valves, which sounds daunting when you think about it, but it's really not. What the 6-way valves do is they take the 4-pipe to a 2-pipe, right? So you've got a 4-pipe heating loop, you got a cooling loop, the 6-way valve based on what the zone, and we did it on the perimeter zones because in the South, we don't really have to put heat on the interior, right? We usually put it on the perimeter. So we have 6-way valves on the perimeter and decides if the zone needs cooling or heating. It provides either heating water or cooling water depending on what the zone needs. And on the interior, we just had it tied to the cooling loop because we just needed to provide cooling in those spaces. We also pulled off of the return water for the chilled water loop for some water source heat pumps that we had in like the lobby areas and the basement. It's a little bit warmer water off of the return water off the chilled water loop, so we pulled off of that to serve our water source heat pumps. This is our schematic for our DoAs units. So our DoAs units obviously fed our outside air into all of our spaces and returned that outside air through the DoAs unit for energy reclaim. It also served our conference rooms where we have displacement ventilation in our conference room. So we deliver displacement ventilation lower to the floor at a little higher temperature, and it goes a little slower across the space to heat and cool those spaces off of our DoAs units. This is just a diagram more of that displacement ventilation. You can see the displacement diffusers mounted at the floor level, and the ventilation air flow is low across the floor, so it does the people in the room, and it's at a little bit higher temperature. So those of you that are not familiar with radiant panels, you know, there's different names, right? Chill beams, there's radiant beams, there's different kind of names for radiant panels. Ours actually, we had an open ceiling, so we had them kind of in the clouds in the open ceiling. If you tour the building, you can see all the piping and you can see everything around the building. But you can actually put these in, pipe them in series. You can have up to 64 square foot of active panel in series. And they only have quick disconnects, right? So they're flex tubing, they're quick disconnects for installation and replacement, and it's PEX piping for the piping. So it's not that complicated for these panels. This shows our six-way valves, what I was talking about earlier. The diagram you can see shows the heating hot water supply and return and the cooling hot water supply and return, basically the four-pipe system, and from that you go to a six-way valve. And so that six-way valve determines if you're going to provide cooling or heating to the zone. So you can see that we can have a maximum of 32 linear active panels in series. See, they're piped in series here for each zone. And then we get into the automation. So our goal was, this is going to be a case study, right? This is going to be a living lab. We want people to see what's going on in this building. So we installed a bunch of meters. As you can see here, we had at least 10 meters on the mechanical system. We had 4 on the lighting system. We had plug load meters, all these sub-meters that tied into our dashboard so that we could see what the building was doing. And so all of this is a living lab so that we could see everything that was going on in the building and understand it. So just a little summary here in terms of things we did. This is kind of our chart of how we performed. 189.1, if you've ever read 189.1, there's a lot of criteria there in terms of site work and irrigation that didn't really apply to us, but we did achieve it in the areas within our project scope. Our site energy consumption, our goal, like I said, was 21.4 kBTU per square foot per year. Our energy model from our design team said we were going to be at 18.5 kBTU per square foot per year. The first couple years, we spent some time optimizing the system, so we haven't gotten that low at 18.5 yet. I think we're around 23 kBTU per square foot per year right now. We're still optimizing some things. There's some mitigation things behind the scenes that I don't have time to go into today, but that's still optimization. Water efficiency, we achieved that. Daytime plug load, we've been measuring that. Acoustics, we had our acoustical engineer come back in. They added some sweeps under some doors and some things to make sure we met our acoustical levels. We met our outside air rates. We've got our demand control ventilation, our daylighting, and our resiliency. So this is our cost. So we started the project with, like I said, a budget of 8.75 for construction. We had already purchased the building, a little over $5 million for that. We had some FF&E costs, some contingency. So our total pre-design budget was $15.7 million. Halfway through design, of course, this goes up because there's other things that we didn't consider that I'm going to go to in a minute. That gets us at 18.1. And then our GMP, our board of directors approved a GMP of $20 million flat out at the end of the project. And so we ended up under that slightly. Lucky for ASHRAE, right? So we had a very good capital campaign that raised quite a bit of money. Plus we had made money on the sale of our building. So really the net cost to ASHRAE was about $3.2 million because the rest of it was covered. We have since paid off that loan, so we don't owe anything on this building. So we had $429,000 left in contingency at the end of the job. Our PV system ended up costing $550,000. So we went through an RFQ process. We got some vendors to give us pricing to lease the PV system or to buy the PV system. It ended up looking at their rates because they were charging somewhere between 9 or 12% interest to lease. it ended up being more cost effective for us to use that contingency budget and a little extra to buy the PV system. So we bought the PV system, as you can see here. We were limited with Georgia with a 250 kW AC system. That's the max we could do in Georgia without hitting some other requirements with Georgia Power. So that was capped, the net metering cap. So we ended up with that size system. As you can see, most of it's on the roof. We have 2 areas on the ground with PV installed. And the estimated energy production is about 457 kWh, which is about 23 kBTU per square foot per year. So we're running tight on net zero. When our building performs right at 23 kBTU per square foot per year and our PV system does everything it's supposed to do for the year, we'll be running right at net zero. And so, lessons learned. Understand the real estate market. We sold our building without looking around first in Atlanta, and a property in Atlanta is pretty expensive. So we were very fortunate to find this building. We looked in Midtown, and a lot of those of you that know Atlanta, you couldn't find a building. I mean, that was at least in our budget. So know your real estate market when you get started on a process. And early goal setting in the OPR, right? So we did a lot of discussions on the OPR before we went out for the design team, before we went out for the commissioning agent or the contractor. So we wanted to make sure that they met our goals. So make sure that gets done. Early budgeting. So we did not plan, when we did our early budgeting, to replace all the windows, to upgrade the envelope as much as we did. So all of that added to our budget, but it ended up being what we needed to do to get us to as low energy use as we could before we added the PV onto the system. And also, we had a lot of existing building infrastructure items that came up during the project that we said, we might as well go ahead and replace them now, right? We got 40-year-old plumbing systems. We got 40-year-old switchgear. We need to probably go ahead and replace all this now. And the fire protection requirements have changed. All of that had to be replaced as well. So there were some budgeting items that came up, as they do in all construction projects, that we ended up going ahead and getting done during the course of this project. So that's just an overview of the project. At this point, I will turn it over to Ken.
Question, you know that you weren't LEED certified, but the project was back in 2019. Yeah. Are you certified now?
No. So we talked about this a lot. There's a lot of certification programs out there. We were actually looking at Living Building Challenge and WELL and LEED. ASHRAE has a lot of industry partners. We didn't want to make anybody angry by not doing one or the other. And it was going to be $160-something thousand to do all the certifications. And we just decided we could do better, have better use of that money somewhere else. So we actually went for our own certification on building EQ. We just got our as operated rating, and it's 0 is the best, up to 100, we're 3. So we and that's not fudged just because it's an ASHRAE program, right? So we just got that actually last month. We think some more optimization is going to get us down to 0, but we just decided it was best not to spend the money on that and to go for our own certification program. Yeah. Other questions? Yeah. The control band, good question. Is it 2 degrees? 2 degrees, yeah. Yeah, lots of feedback from that. Some people don't mind it. Some people think it's too warm. We actually had some directors' offices that we did not put ceiling fans in. And we ended up going back and putting ceiling fans in because of that set point. So yeah, there's always, as you know, in buildings, some people are hot, some people are cold. So yeah.
People having papers on their desks, did they just fly up and stuff?
Well, so they blow at a really low speed. They do speed up over time, but I've been in there working many times, and it's never been an issue with anything. And plus, most days, people don't have a lot of papers. They have their computers, and it doesn't impact a lot of that. Now, I can tell you during COVID, because we had our COVID response team, right, our ad hoc that was doing all of that, Because they evaluated our building for health and safety during COVID, right? So because we have 100% outside air through our DoAs, that was like we passed challenge number 1. We don't recirculate air through the rooms. They also said turn the ceiling fans around so the air blows up. So we did that so it doesn't blow down on people. So if somebody's sitting over here, it doesn't blow down on them over here. So they evaluated our building for health and safety during COVID. That's the other thing that happened in the middle of this construction project, right? COVID. So we had to be out. We were very worried about our contractor being able to finish the job because everybody was out. We couldn't get materials. COVID was happening. It got done. It got done on time, and it was a real nail biter there at the end, but we got it done. So.
Just wondering, how big a part did unoccupied setback scheduling of AC systems figure into the, how big a part did unoccupied scheduling of AC systems, night setback, weekends, play into the net zero?
I would say a lot. I'm going to let Ken talk about that in terms of the controls. I can tell you that for the first 6 months plus, Daryl, or so, there was no setback in place, and we had to go back and get that done. So our energy use didn't account for that at that point in time. We've since corrected that issue. So there was a lot of commissioning and controls items that had, as you guys know, that our commissioning agent controls are a love-hate relationship.
That was part of your optimization,
it was.
ongoing optimization.
It was. We also had issues with our DoAs units and some humidity control and the sizing of the DoAs units, and some of that had to be resolved. So as with any construction project, it was a work in progress. So yeah.
And one more small question: were they high volume, low speed ceiling fans,
They
or
were.
the more? So,
They were.
Yeah. Thanks.
Any other questions? Okay. All right. Sir. Yeah, so yeah, we got our outside air 30% greater than required by ASHRAE 62 with the DoAs units.
How did you do that?
With our DoAs units, we sized them for 30% greater, which, as you know, is a higher energy use, right? But that was something that our technical advisory subcommittee felt like we needed to do. Okay. The demand ventilation in the space. So we have, I don't know if the set point, you have to check if it's 800 or 1,000 parts per million, whatever, on the monitors. But we have demand control. We have, CO2 monitors in the space that we monitor the conditions of the, yeah. Does that answer? When they ramp up, we are. Oh, we got to wrap up. Sorry, I'm sorry, I took you long.
One thing that I do want to point out, Ginger kind of alluded to this. This is, I don't know, this project was probably the third or fourth one that I have been involved with in the Southeast that used radiant panels. And so to Ginger's point, with mechanical contractors, there is a real lack of understanding of how these systems work. Most people are used to, the typical or traditional forced air system. You can relax your setbacks quite a bit at night, and you don't have to be concerned with getting the building, quote unquote, back under control the next day. When you have a system like this, you do need to maintain some tighter control. You can't relax the setbacks as much, but if you have that tighter control, you can do it, and you can use the displacement ventilation in the radiant panels and keep the people comfortable in the environment. The other thing is even not just mechanical contractors, but these six-way valves put everyone into a freak-out mode. And we'll look at that here in just a little bit. But just in simplistic terms, just think about the six-way valve as being 2 3-way valves put together. That's it in a nutshell. If you can get your head wrapped around that concept, you're good. But mechanical contractors were struggling with that. I will even tell you the controls people with automated logic were struggling with that. And I spent quite a bit of time trying to sit down and explain that to them. So I'll quickly just go through the user interface. It's using web control. Well control has the ability to do third-party integration. So like at this site here, we're integrating DoAs units, we're integrating PV, we're integrating meters, we're even integrating to the Belimo valves into the ventilation fans that are in the spaces. And we'll look at that here in just a minute. So with this, we have kind of the main page where you can see what's going on. The green is, we call it thermal graphics. This is basically showing, hey, the spaces are good and satisfied. And then we've got basic information on what's going on with the chill water system, what's going on with the hot water system, outside air temperature, energy usage, all that type stuff. So this is a picture of the chiller that's sitting outside. And like Ginger said, this is a modular chiller that is capable of doing simultaneous heating and cooling. And this is where the real fun happens. So this is the diagram showing the chill water loop and the heating loop. As Ginger said, it's a primary, secondary system. Now, one of the challenges we had here, I don't remember the exact details, but with the chiller, particularly on the chill water side, we had to maintain a different set point on the secondary loop than what was on the primary loop. So we've got a mixing valve to help provide that temperature difference between those two loops. And that had to do with the challenge with how the chiller was operating. And with the chiller, the points that you see on the chiller itself, we did integrate to those and bring that information in. And then like Ginger said, on the hot water side, we do have where we're pulling water off for the water source heat pumps that are like in the public areas. This is one of the DoAs units that's at the campus. So we have an east and a west DoAs unit. This is a complete integration. So all these points that you see are integrated directly from the DoAs unit and brought into the BMS system. And as a BMS system, all we're doing is providing set point control and then monitoring all the points that are on the DoAs unit. These are the Sixway valves. So you can see, like Ginger said, you've got basically a 4-pipe system coming into the Sixway valve, and then it gets converted, and then it sends, hot water or cold water to the radiant panel as needed based on the zone request. And like I said, I really want you to understand the fact that basically you have 2 3-way valves that are basically inverted, that are stacked or side by side, and that's how they work. So you're either sending chill water or you're sending hot water to the zone based on what that request is. But for whatever reason, that scared a lot of people, and I think that did drive particularly some of the installed costs because contractors just didn't know. And I've actually seen this happen, like I said, on about 3 other projects. It was the same phenomenon. Yes?
Or can it mix and kind of send the temperature needed?
It is going to blend the way it works. They are, I guess, what you would call a mixing type valve. So, but it is 2 3-way valves that are inverted.
You're running that on a pit loop? You're running that on a pit loop to maintain
The
Temperature.
discharge?
To maintain the temperature
Yeah,
in the
okay.
zone. Correct. So this is a picture or a graphic of the ceiling fan in the 6-way valves. So you can see there on the left, we've got information that's coming from the 6-way valve. We have integrated to those Belimo valves, and that is all information that's coming off the valve. One of the things I do want to point out on these 6-way valves, they can be set up for what's called flow control or position control. Flow control is just going to be controlling based on the GPM that's going to be required. Position control is going to be based on position of the valve. These are set up for flow control. And in these ventilation fans, they are, high volume, low speed fans. We have integrated to them. We can change the direction so they can run in forward or reverse, and that speed is based on what's required in the zone. We have also integrated to all the power meters. This is just a diagram that's in the user interface at the ASHRAE building that shows where all the various meters, and you can click on that meter and get the power information from that meter so you can see what is going on with that power meter. We also implemented a CxEnergy reports portion to this. This is something that resides in the cloud, but with this, we're able to create some energy dashboards. So we're right here, you can see where we're able to see the electricity by load. So Ginger mentioned, we're able to look at lighting load, we're able to look at plug load, and then we're actually able to look at what's going on with the mechanical load in the space or in the campus. And then in terms of net energy, we're also monitoring what's going on with the PV system. So you can see starting in February, we're trending towards basically all the power that the building needs is coming from the PV system. We're not pulling it off the grid. So any questions to the user interface? Yes, sir.
Yeah, so, you have the DoAs unit, which said would be neutral. You have the radiant, and then you have your fans. So what is your hierarchy of control? And when the DoAs says that it's neutral, is that then tracking the temperature of the space to be truly neutral?
No, the DoAs is always producing neutral air all the time.
So neutral as in tracking along with whatever the space set point is?
No, neutral as in it's producing neutral air all the time. I have to go back and look at the set point, but it's probably going to be somewhere in the neighborhood of like 72.
So with your DoAs, how do you control the conditions of which the discharge on the DoAs are occurring? I'm sure you have an outdoor sensor such as a dew point sensor that's doing that, and do you have more than one dew point sensor?
The DoAs is doing all of its control internal. And so you can see it's got the DX system and electric heat for trimming out, and it is using its own program inside to control what it's doing.
Right, and it's a fixed discharge temperature, right? Humidity.
Right, but your outdoor conditions change.
It doesn't vary the discharge temperature or humidity. It varies the airflow that's needed for making ventilation, but it doesn't vary the temperature delivery off the way. Okay. So everything in space is handled with fans and radiant panels. We just deliver the humidified neutral air.
Right, so call it 72.
Yeah.
Right, because that's what the question was, neutral meaning is it tracking along with the actual space set point and trying to dive up, down, down. So then when you, taking that aside, what's your hierarchy for the fan and the radiant? Is it fan first, radiant first? How's that all?
It's going to be radiant first and then fan second.
Thank you, guys.